Okay, recording started. Very good. Now, let me share the screen. And I want to quickly try to conclude the discussion on decision theory, and in particular the discussion on analytic hierarchy processes. Just 1 second, I open the PowerPoint, which is easier a little bit. So let's see. Okay, good. The right slide is this one. Okay, this is the problem that we were trying to solve, and I just would like to make a brief recap of what we discussed in the last part of the lecture, which was a little bit quick. Remember that we have 3 alternatives and 4 criteria. So the final part of Monday's lecture was focusing on the weight to be assigned to the criteria, the W's, okay? Because our problem is that we have 4 criteria, and we aim to put them together by assigning to each of them a weight in order to identify what is the most important of these 4 criteria and what is the order of priority. And the weights, by definition, should sum up to 1. So if we have 4 criteria, the sum of the 4 weights should be 1. The same would be if we had an arbitrary number of criteria. And in order to determine this weight, we said that we adopted the method of pairwise comparison. We compared the weight 2 by 2 and tried to identify what is the importance of an assigned weight with respect to another one. And we repeated the same comparison for all the possible couples of weights. And the scale, which we suggest to use, it is suggested by this method, which was proposed by Satie in 1970. It's the scale that you can see on the screen, which means that if you compare 2 weights and you want to give equal importance to each of them, the first with respect to the second, you say that the score is 1, the intensity of importance is 1. And then if you want to give priority to the first criteria with respect to the second, you adopt a score larger than 1, where 3 means moderate importance of the first with respect to the second criteria, and then 9 is extreme importance. And you can use any number in the scale between 1 and 9, and also you can use the reciprocal numbers. If you want to say that the first criteria is less important than the second, moderately less important, you may say, you may use the score of 1/3. So the reciprocal is, which means less than 1, means that the first criteria is less important than the second. And then we put this comparison into a matrix. This matrix here is just an example. What is, there was a question which I want to recall here. And the question was, when I make this comparison and I build this matrix, so let's see if I have the opportunity. Let me focus on the screen, because if I use the blackboard, I have to bring the camera there, it's a bit complicated. So when I compare the criteria, and for instance, a very trivial comparison between the net benefit and the environmental impact here. The question by one of you was, should I consider as first criteria to be compared the one that I find on the left column or the one that I find in the upper row? So if I want to compare net benefit with environmental impact and I put a score of 7 here, does this 7 means that net benefit is more important than the environmental impact, or should I take the other way around? Environmental impact is more important than the net benefit. And my reply was, let's start from the column, okay? What I want to say now, because I thought of it, it doesn't matter if you start first with the column or first with the row, provided you are consistent when you travel through the matrix. So you may also say, in this case, that you are comparing environmental impact with the net benefit, but then I should have put 1/7 here. Okay, because this matrix was built by considering that I am comparing net benefit with environmental impact. You can also take the other direction, but then you have to put the reciprocal here. And then keep in mind that when you go to the anti-symmetric position, the symmetric position in the matrix, so when you compare the environmental impact with the net benefit, by definition, you should put the reciprocal number here. So here you see I gave us a score of 7. Net benefit is more important than environmental impact. When I make the comparison, environmental impact against net benefit, I have to put the reciprocal here. So if I started as first term of comparison with environmental impact, I should have put 1/7 here and then 7 here. It doesn't matter which direction you take. The important thing is that you are coherent, okay? So my suggestion was, let's start as first term of comparison with the column. So net benefit against net benefit is 1, okay? Perfect. Net benefit against environmental impact, I gave a score of 7, which means 7 means, just 1 second, very strong importance, okay? And then net benefit with respect to river flow regime. I gave a score of 4, which is 4 is between moderate and strong importance. And then net benefit with respect to the CO2 emissions. Again, the net benefit is more important, okay? Now, let's go to the second term of comparison. So, environmental impact with respect to net benefit. We did it already, so it's 1/7, okay? In the diagonal, we have 1. Environmental impact against environmental impact. Perfect. Now, environmental impact with respect to river flow regime. This is a good question, because I should try to be consistent. So, for instance, if I look at the previous rows, if the net benefit is much more important than environmental impact, but only more important with respect to river flow regime, it means that implicitly I declare that the river flow regime is more important than, am I correct? Yes, than environmental impact. It's more important. Okay, by consistency, because if I compare these two, you see that 4 is less than 7, which means that this one is really the last one. Now, when I compare then the environmental impact with the river flow regime, for consistency here, I should have placed a number less than 1. So this matrix apparently is not consistent. Now, let's make the same reasoning with respect to the CO2. The CO2, when I compare environmental impact with respect to CO2, should be less important. Less important. In fact, environmental impact with respect to CO2 is less than 1. This is consistent. Okay? And then, let's go to river flow with respect to CO2. River flow with respect to CO2, I would expect a number greater than 1, based on the first comparison that I made. Here I have a number that is less than 1. So it apparently is not consistent. So you see that it's a bit tricky, and if you imagine a discussion with 20 stakeholders, it becomes a bit complicated to move forward through this process to ensure consistency. First, keep in mind that once that you build the part of the matrix that is above the diagonal, the part that is below the diagonal is automatically big. So you are going to concentrate on the part of the matrix that is above the diagonal. And the other part is just the reciprocal numbers. Please.
So you're saying this matrix is not consistent?
Yeah, I'm saying that apparently is not consistent. So, but you know, if it is not easy to interact with you to prove this, you can imagine that with an audience of stakeholders is more difficult. And therefore, the suggestion of this method is, let's forget about consistency for a moment. The important thing is that I can test it, because I anticipate the result. If the matrix is not consistent, the weights are not reliable. So, I mean, at the end of the process, it's important that the matrix becomes consistent. On the other hand, the discussion may be complicated. So, in this case, I think the analytical procedure, the math part of it, becomes supportive. Because we can say, okay, if you are convinced by this matrix, stakeholders, that's fine. And you may say, in my opinion, maybe not consistent, but okay, if you are convinced by it, that's fine. And then you apply the test. And the test proves that it's not consistent. And then, after the test, you may discuss with the stakeholders to identify why it's not consistent. And then you may make the reasoning that I just made with you. Like, when you compare the net benefit with the environmental impact, you said that the environmental impact is much less important. The river flow regime, you said that it's less important, but not so much. Which means that you are giving more weight to the river flow regime than the environmental impact. So when you compare the environmental impact with the river flow regime, you should have put here a number less than 1. In general, when you entertain such a discussion with the stakeholders, you know, if you have several criteria, it becomes a bit complicated. You can imagine here, if I just had 3 criteria, not 4, it would be much simpler. With 2 criteria would be trivial. No need to adopt this method with 2 criteria. You just discuss, okay, so net benefit with respect to environmental impact, which weight should be used, 50-50 or 60-40, 70-30. I don't think you need really a mathematical procedure to determine this. You can make an agreement, okay? And if you have 3, it's a bit more difficult, but not so much. If you have just a 3x3 matrix here, it will be much easier. 4x4 becomes a bit complicated. If you have 20x20, it's a bit complicated. And but there is a logic in the compilation. Even if you had a 20x20, you see that I can explain if the matrix is consistent or not. I can make a reasoning on it. There is a logic, okay? So you have to try to use that logic. And let's make an assumption for now. Let's make an assumption that we fill the matrix randomly, okay? With the only condition that you have 1s on the diagonal and the part below the diagonal is the inverse of the part above the diagonal. We can fill it randomly. And randomly, of course, you expect that it's not consistent. Why I'm saying this? I'm saying this because a random fill of the matrix may be a term of comparison. If you find a way to quantify the intensity of consistency, let me adopt this term in an informal way, to measure consistency, the random matrix may be a term of comparison. Like, okay, I generate a random matrix, I identify a way to measure consistency, and then with the matrix that was filled with the logic, I can make a comparison. And this is precisely the aim of the test. This in general is the aim of statistical tests. Many statistical tests are simply a comparison between a model and randomness. So you make a model of something, and then you compare the model with something that is random. Statistical testing is basically based on that, with different level of complexity. Now, the problem is, if we want to make this kind of comparison, the problem is how to measure consistency. And this is what we started just in the last 3 minutes of the lecture on Monday. How to measure consistency. And here there is, as I said, a mathematical procedure which we don't need to understand in detail. We need to understand the logic. Keep in mind that this is for an engineer or in general for a professional, for a policymaker. The important thing is to understand the logic of the model that they are using. It's not important to understand the full math. And like, for instance, again about statistics. We said with climate change we need to use statistics. But it's not needed that you, as a policymaker, as an engineer, take a master's degree in statistics. The important thing is that you understand why you need statistics and why and the logic behind it. So there is nothing wrong if I say now, let me just tell you how consistency is measured, but forget the details. The important thing is that you understand the logic, and the logic is precisely a comparison with a random matrix with some measurement of consistency. Okay, so how to measure consistency? First of all, let me say how to measure weights. Just in order to make it clear, because it's simpler. The weights are given by the matrix principal right eigenvector. So, again, it is very easy. We may spend 5 minutes to understand, to recall you, because you studied what is a right eigenvector. But I don't want to make it, I don't want to spend these 5 minutes. Not for the 5 minutes in themselves, but because I don't want to generate confusion. A matrix, it is easy to identify the eigenvector of this 4x4 matrix. You can use R, you can use Excel, and I hope that I wish I had time to introduce you to a very simple Excel sheet in order to identify. Maybe that we can take 5 minutes, that is available, is linked in my webpage, in your webpage of the course. It's linked, you can download it, and it is easy to identify in Excel and in R the elements of the right eigenvector. And they don't sum up to 1, so you have to rescale them. It is very easy. If they have a sum that is 2, then you divide each element, each weight by 2, and their sum goes to 1. So you just have to divide each element of the right eigenvector by the sum of the elements themselves, and you rescale them to 1. And these are the weights, okay? But the weights may be not correct. So let's try to now estimate consistency, and the screen is not complete, but okay, we are just losing a letter here, so you have to trust me. I'm reading the letter. I don't think it is easy to, I don't want to lose time. Let's try to move forward here. In the ideal case of fully consistent matrix, now let's focus on the eigenvalues. One thing is the eigenvectors, and another thing is the eigenvalues, which in Italian are called autovettori, just for the benefit of the Italian students. So these eigenvalues, they are 4 in a 4x4 matrix, and we take the max. Okay, and so in a fully consistent matrix, the max eigenvalue is equal to the dimension of the matrix. And the dimension of the matrix, here there is written 3. Actually, we dealt with the matrix with dimension 4 by 4. So here there is a mistake, okay? It's 4. Okay, if the matrix is not fully consistent, then we can compute an index of consistency, which is given by lambda max minus n divided by n minus 1. This is the measure of consistency. So maximum eigenvalue minus the dimension of the matrix, and this difference is 0 if the matrix is fully consistent, divided by n minus 1. So if the matrix is fully consistent, then the index of consistency is 0. There is a question here.
Where can we find the eigenvalue?
The eigenvalue, yeah, it is can be computed in Excel or R with a simple procedure. Maybe that we can open the Excel file and I show you. Okay, perfect. Now, so let's postpone it. Just keep in mind that eigenvectors and eigenvalues in Excel or in R, they can compute it easily. So this index, again, if it is 0, the matrix is fully consistent. Okay, good. Now, we can compute what is called a consistence ratio. The consistent ratio, CR, is given by the ratio between the consistency index divided by the consistency index of a full random matrix. And therefore, the consistency index of the full random matrix is expected to be different, larger than 0, and you compare it with the consistency index of your matrix. And then there is a table, which you can see here, which gives the max of, the table gives to you actually Ri, which is the consistency index of the random matrix. And it depends on the dimension of the matrix. The table goes up to a dimension of 9. And then, if the ratio CR is less than 0.1, then we can consider the matrix consistent. If it is 0, it's fully consistent. If it is larger than 0, the consistency index, then you have some loss of consistency, but if the consistency ratio is less than 0.1, you can take it as consistent, okay? If the consistency ratio is larger than 0.1, then you have to go back to the matrix and improve it. That's it. Now, I think that now we can move to an example of application. We have some time. And with the theory, I think that we can close our discussion here, which means that up to where we got up to today, you may get questions at the exam, and beyond that, no questions. And as I said, I will put some links in the web page I will make it clear that these links are only for your information. Okay, because there are other links that I want to give to you, only for your information. Okay, now I will pass to the application, but do you have any question? Okay. Let's see. I go back to the web page. So here, let me see if decision theory it's finished with the Yeah, it's finished here. So here in the web page, the last link that you will have to study is decision theory. We did it. And then I will put the design of climate change adaptation actions in the separate list of links for your information only. Okay. Good. Now, if you look at the exercises, there is application of pairwise comparison for decision making. Okay. Let's look at the text first. Okay, so it is an application to estimate the design flow of a run-of-the-river hydropower plant, and there is written here, a small hydropower plant with no regulation. I apologize. A small hydropower plant with no regulation is to be designed for a cross-river section. The design flow can assume only specific values. So these are the alternatives. In terms of liter per second, 80, 90, 100, 110, or 120. So these are the alternatives. Okay, it's a different example with respect to what is reported in the web page. Here the 5 alternatives are 5 values of the design flow. After a careful assessment of the environmental and the economic behaviors of the project, the following indicators have been identified for evaluating the most appropriate alternative. Economic benefit, indicator 1, the impact on the fish community, indicator 2. This is an indicator that is often proposed by the fishermen. The impact on the landscape, indicator 3, the fruition of the downstream river for recreational purposes, indicator 4. This is another indicator that is often introduced. When we take water from a river, of course, people are also concerned by the impact on recreational activities. So the utility function associated with the above indicators, depending on design water withdrawal, are piecewise linear functions, this means that we have to give utilities. You remember the utility function that we used to give a utility. In this case of this exercise, we give the utility of each alternative in terms of design flow with respect to each indicator. So the indicator 1, the economic benefit, is given by these utility functions, this utility function. And basically, it's a piecewise linear function. You have utility 0 in terms of economic indicator for design flow which means withdrew flow 0, and this is perfectly understandable. If you don't take any water from the river, you don't produce any energy, and therefore you don't have any utility in terms of economic benefit. And then you have a utility 1 associated to a design river flow of 150. But the utility remains 0 up to a design flow of 30. And this is something that for hydropower plant is justified. I mean, if I design an hydropower plant, I have to take a minimum amount of river flow in order to justify the project, to justify the expenses. So if I take a river flow that is less than 30, I don't have any economic benefit from it, and therefore I give a utility 0 up to a river flow of 30, and then I have a linear increase from 30 to 150. 150 is max utility, which means that even if I were able to take more than that, I wouldn't get any additional benefit. For instance, because I don't have the opportunity to sell the electricity after a certain value. So the utility function in this case allows me to quantify with respect to each indicator the utility of any alternative. Now, indicator 2, what is the indicator 2? The impact on the fish community. What do the fisher persons say? The fisher persons say, I give the max utility to no plant, max utility to no withdrawal of water. So, with a withdrawal of 0, I give the max utility. And I keep this max utility up to a withdrawal of 60, which means that even if you take 60 liters per second, still I can live with it, with the max utility. And then for 150, I have a utility 0, which means that if you take 150, really, I don't go anymore to fish on that river. So utility 0. We will plot graphs for these functions. Just wait for a second. Indicator 3. Indicator 3 is impact on the landscape. Same thing. Max utility to no plant up to a withdrawal of 100 liters per second. So I can live with, from the point of view of the landscape, I can live with it. Landscape, you know, when you look at the landscape, if you see a dry river, it's not a nice view. So you are not happy if some water is taken by the river. And therefore, but in any case, up to a withdrawal of 100 liters per second, you can live with it. And then for 150, utility is 0. The indicator 4 is the fruition for recreational purposes. Again, max utility for no plant, up to a withdrawal of 10 liters per second. So, I mean, these utility functions give a clear picture to you of what is the impact on the indicators of the plant. Now I have to give weights to the indicators. Because now I have quantified the utility for each indicator, but I have to put them together, okay? So the optimal river flow withdrawal should be identified by using pairwise comparison, by making sure that the evaluation is consistent. I have all the elements here to carry out the evaluation. I have the utility functions and I have the indicators. I have to compute the weights. Okay, now let's go to the zip file again, and here actually I don't have the Excel, but there is a R code, so let's open it. And let me see. I hope that I have R here. Otherwise, it's relatively easy to install it. Give me 1 minute. Okay. Let's install it in English. Okay, good. Next, 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 next. Okay. Okay, let me open it now. Okay, let me just change the font because otherwise it's too small. Okay, good. This is the R console that you know, okay? So the first thing that I have to do to solve the problem, I have to put into R the utility functions. And in fact, the first part of the code, which you see here, is the definition of the utility functions. I have to change the link here because the link is not correct anymore, but this is just a detail. So definition of utility functions, let me copy them, and then I make a plot so you can see that I made a cut and paste. Okay, good. So let's see the utility, the function u1. In order to plot it, let me see what is u1 80, because the utility function is to be computed for each alternative. Okay, this is the utility of 80. And in order to make a plot, I think I should do this. Plot. Let me think. On the x-axis, I think I should make 80, 90, 100, 110, 120. This is the horizontal axis. And then the vertical axis is C, U1 80, U1 90, U1 100, U1 110, U1 120. Let's make it as a line. We are expecting, just 1 second. Okay. We are expecting a straight line here. Okay. This is the utility function, the utility for each of the alternatives starting from 80 and ending to 120. You remember that the utility was 0 up to a value of, I think, 30. And therefore, you see that for a value of 80, the utility is 0.4. And it was 1 for a withdrawal of 150. So for 120 is about 0.75. This is one example of utility function, just to show you that we have put them into the correct format. It is easy once that you plot the first. It is easy also to plot the second. And for instance, we may put here U2. U2, I think that this is for the second indicator. It should be a decreasing function because the second indicator is a decreasing function. In fact, you see here. And the same for the third indicator, should be a decreasing function. These are, as we said, piecewise linear function. And this one, you see, is piecewise. Utility is 1 up to a withdrawal of 100 and then decreases. It's piecewise linear. We just introduced the utility. Any question? Okay, now let's move forward with the weights. And now we have to define the matrix of the pairwise comparison. We have 4 indicators. So first, let's define the matrix by filling it with zeros. I call the matrix prova. Okay, prova means attempt in Italian. And the matrix is here. You see, for now I just filled it with the zeros. Okay, and now let's define the matrix. First of all, let's put the diagonal elements equal to 1. Oops, sorry. So you see that for now I just filled the elements in the diagonal. Okay. Now let's move forward. And then the scores. These scores, you can change it as you like. I mean, let me just input it into R, and then I show you the matrix, okay? So this is the matrix so far. I just filled it with elements above the diagonal. And I mean, you can use the numbers that you like. It's just an attempt, okay? And then I have to fill with the inverse the number below the diagonal. Now this is the resulting matrix. Now it's completed, okay? Okay, is it consistent or not? This is the question. And then we try to play with it, okay? We can put other numbers. Now let's see if it's consistent or not. First of all, the eigenvectors. The eigenvectors are computed with first this instruction here, eigen prova symmetrics false, because this is not a symmetric matrix. Oh, yeah, okay, sorry. Okay. Okay, I also need to move, I'm sorry for that, I didn't see it. I also need to move this. 1 second. Too many windows. Okay, good. I'm sorry that you didn't see clearly before than that. Okay, let me just, 1 second. I'm trying to reorder the windows in the correct way. Okay, so let me just increase the font. Okay. Now you see if the instruction is eigen, name of the matrix, symmetric false, and then let me copy it. Oh, sorry. Okay, and to compute the eigenvector, the instruction is this one. The instruction is this one. It's the first part. The selected part of it that you see on the screen is the instruction to compute the right eigenvector together with the previous one. And now if you look at the result, the sum is larger than 1. This is the right eigenvector, but the sum is larger than 1. So I have to rescale it. And in order to rescale it, it is very simple. I can write pesi equal pesi divided by sum of pesi. And now the sum is 1. Now if you make sum pesi, it's 1. So these are the resulting weights for the 4 indicators, which were, let's go back to the text. 1 second here. The 4 indicators: economic benefit, impact on the fish community, impact on the landscape, fruition of the downstream reach. These are the 4 weights. Basically, we give the same weight to the economic benefit and the impact on the fish community. We give a reduced weight to the landscape and a large weight to the fruition for touristic purposes. Now, we need to check if the matrix is consistent. If the weights are confirmed, what can you get from this? As an anticipation, because as I said, you have to get the logic of it. You better drive a decision with the stakeholder if you fully understand the logic of it. And the logic is that if you give half of the total weight to the touristic recreation, and also you give a significant weight to the fisheries, you are expecting that the best solution is not the larger withdrawal. You expect a penalization of it. Still, given that there is some weight to the economic benefit, you expect that the decision is not zero, is not no plant. Okay, but first let's see if it is consistent. And then in order to see if it's consistent, we have to compute the eigenvalues, and in particular the max eigenvalue. So let's look at the code. So this is the CI. If you remember how CI is computed, it's max eigenvalue, and you see a max function here. There is an instruction to get the eigenvalues, minus the dimension of the matrix, divided by dimension minus 1. Okay, so let's try to see what is the result. One is 0.01, but now I have to compute CR. And to compute CR, I have to go to the table here. To the table for dimension of 4, Ri is 0.9. So now I have to compute CR, which is CI divided by Ri. So let me go into R. CR is equal to C1 divided by 0.9. What is R is 0.01, so it's less than 0.1. I am happy with the consistency. Then let's compute the best alternative, and then we try to check the consistency for a matrix that we fill in a stupid way, okay, just with random numbers, and we see what comes out, okay? But before that, let me compute the best alternative. Now I have to multiply the utility function for the weights, each utility function, and then this is done in this way. I multiply basically any utility by the weights, and the U is the matrix of the 4 utility functions. And if I multiply this matrix by the weight, I have multiplied the utilities by the weights, which is what I have to do to put together the scores of each indicator. And then I can compute the score of each alternative. See what are the scores of each alternative then. See that the best score is for the lower alternative, which is what we expected, given the weights. Now, let's try with a different matrix, and let's try, just for fun, to give the max utility to the net benefit, the max importance to the net benefit, okay? The max important in the pairwise comparison. Let's see what happens, okay? Now, in order to do that, I need to, let me clear the screen, I need to go back to the instruction of the definition of the matrix, which is this one, and in particular this, okay? I need to change this. Unfortunately, I cannot change here. Oh no, I can change here, very good. So let me just, this is my original matrix, and in the pairwise comparison, basically I think I did, okay, let's say that the net benefit is the first indicator, okay? So the net benefit with the second indicator, which is the fisheries, let's say that it's more important, much more important, 9. Good. And then net benefit with the third indicator, max important. Net benefit with the fourth indicator, max importance. Good. Now, the other indicator, so I put the net benefit just much above the others, and the other I put them at the same level. So let's fill, given that the others are at the same level, with ones, the other scores. Here is, I think it's okay, because here the instructions are just imposing the inverse values. So let me copy these ones and these ones. Just in order to repeat what I'm doing, I'm giving the max weight to the net benefit. And the other indicators, I put them at the same level. This is very simple to do, okay? Good, let's do it. So now the matrix is this one. It's very simple, okay? It should be consistent, actually, because here I adopted a very stupid way, a very stupid solution for filling it. So, first of all, I compute the weights here. And let's see the weights, okay? And I am expecting the max weight. You see max weight to the first indicator, which is the net benefit, and then the other indicators at the same level, very low weight. Okay, good. And now I can compute the consistency. Yeah, it's consistent because as I said, I took a very stupid way of filling it. Okay, and then computation of the best solution. What I am expecting here, I am expecting to get 150. The 120 is the highest alternative. Perfect. Now let's try to fill the matrix in a very stupid way and see if it is consistent. Okay, and let me go back to the definition of the matrix. The matrix is, by definition, with this instruction, is putting the inverse below the diagonal. And what I have to change is this one. Here I go just by, 1, 1/9, and then here I put 5, here 2, and here 1/2. I just went by chance, by pure chance. If this is consistent, I would be surprised, okay? Matrix, okay, just random. And that I filled it randomly, I am expecting a value of CI, which is close to the random value of 0.9. This is what I am expecting. Let's see. I compute eigenvectors, the weights, and the CR. You see, it's absolutely not consistent. Is also less consistent than a random matrix. Yeah.
Why are we filling the matrix in a way where we believe it might be consistent and check it rather than compute the rest of the values so that it's always consistent?
So you say, why shouldn't we try to fill it in a consistent way?
Okay, and I'm saying why don't we fill in the first row and then have the rest be filled in by, I don't know, generating an equation that always improves consistency, or is that not possible?
Okay, you know, it's possible. I mean, if I well understood, I have to go back here and Okay, let's take the first row, okay, in this way. And then the second row, let me try to go on the blackboard because so you want a matrix that is in a way we make it consistent to our text. Okay, we fill the first row and then we try to make it consistent.
So we fill the first row and then all the rest is computed in a way, calculated in a way where it's always consistent.
Okay, computed in a way to ensure consistency.
So the first three of the values are filled in, and the second three are calculated based on the first three, so that it's always consistent.
Yeah, I think this can be resolved only with the trial and error. So you may generate, okay, you take the first three numbers, and the other three are generated randomly, but then you compute consistency. You make a median of attempts, and then you pick up the one that is closer to consistency.
But if I fill in the first row, I already know that the ratios between the other parameters as well, don't I? Because if I know that, for example, in the first row, column 2, we have importance 9, and the third one is importance 1. So we know that 3 is more important than 2.
Yeah.
So I can also put a value in the second to last, which ensures that 3 is more important than 2.
Yes, correct. I understand. So basically, you are suggesting to do precisely what should be done in reality. So in reality, you should, in the first row, it's quite simple to be filled. Let me see if I can. And I ask the students who are attending online to be patient a little bit because I am recording on the screen what I write, so on the blackboard. So basically, I have, let me use symbols. Okay, I1, this is really, okay, there's another one here. I'm sorry, I need to go on the screen. So, let's keep the first row. So here I put the first indicator is much more important than the second, strongly more important. At the same level as the third and much less important than the fourth. Now, when I compare the second with the fourth, I would say that the second is much more important than the fourth. So I should put a 9 here. And then the third with the second, which means the third with the second should be less important. Let me see, the third with the second, yeah, less important. And the fourth with third, it's 9. I'm not sure. We should think of it. It would be better to write on the blackboard because here the position is not very clear. This could work. Let's see.
But 3 should be more important.
3 should be more important than 2. Let me see. 3 should be more important than 2. Correct. Correct. And then 3 to 2. Let me see. I think.
Also 2, it needs to be more important than 4. 4 needs to be more important than 2, so the third one, I don't know if it's correct, putting 9 is the third one.
Okay, let's see. 1, 1. 1 over 9. Yeah, I think 1 over 9, let's see, because if this is more important and less important, yeah, this one I think should be less than 1. Do you agree? 1 divided by 12, maybe. Let me try in this way, okay? Let's try mathematically. Oh, it's not consistent, so there is something wrong here, but I think we should write on the blackboard, but I don't have any opportunity here. Or I should, let me check if I can. Okay, it looks like the touch screen works. Let me make an attempt, because I think we have to draw the matrix, otherwise it's impossible to get give me 1 second. Okay. Okay, let's try to work on this. So, no. Okay, let's use it in this way. Okay, now let me check here. 911.9. So this is 1. This is 1. This is 1. This is 1. Perfect. And here I have 9. And here I have 1. And here 1/9. Okay, this is the first row. And then let me put here we have 1 over 9. And then here we have 1, here we have 9. I'm just filling now the antisymmetric. Okay, now we have to make this comparison here. So this is let me check. It's the comparison between the second and the third. So the second and the third, I think I should put a 9 here. And this is a comparison between the second and the fourth. And I should put here something like 18 or something like that, or 15. Do you agree? Just check what I'm doing. And here we are comparing the third with the second. So the third with the second is less important. So I think, or let me see, this is position. I think what is missing is just this one.
Could you explain the 15?
Because I mean, if the first with the fourth is, the first with the third is equal importance, and the first with the fourth is less important. So here, I think it is the second with the third is clear, and the second with the, because when I compare the second, which is I understand. The second with the fourth. Yeah, it is not 15. It is less than 1. So 1 over 15 maybe. Okay. And now we have here 1 the third indicator with the fourth, the third with the fourth should put a 9 here, correct? Yeah. No, not a 9, but a 1/9. Let me check. Because the first with the third is the same importance, but the is less important. So the third is less important than the fourth. Okay. I think in this way should maybe work. Now the problem is that we have to translate it here. So 9, 1, 1/9, perfect. 2, 4. 2, 4 is 1/15. And then there is 3, 2. 3, 2 is just 1 second. 2, 3. 3, 2 is 1, 2, 1, 3, 1, 4. Okay. 3, 2 should be 3, 2 is 1/9, I would say, because it's 2, 3. Yeah, 1/9. It's not easy to make these attempts just in a few minutes, because of course 4, 3 is 9. Let's see, and if I am not successful, we need to move forward. We don't have time to dedicate to this exercise. We don't have more time to dedicate to it. Yeah, it's much better, but it's still not consistent. So I think there is a ratio that was wrong here somewhere. Anyway, the concept, I think it is clear, and it can be done also in Excel. The only thing that you need to, in Excel it is a little bit better because you see the matrix, like in the PowerPoint here. I'm not sure, I think in this matrix, the matrix, I think it is correct as you see it on the screen. What was wrong probably is the translation into these instructions, I think. Not the inverse, but it's the translation just, I think we would need to think some more on the input of the matrix into R. In Excel is easier because you see the matrix. And in Excel it would be just fine to make a cut and paste from PowerPoint, and it would be automatically placed into Excel. I didn't attach the Excel file. You should look into Excel. It is very easy for the instruction to compute the eigenvector and the eigenvalues. It is easy, but you have to look on the web for getting the right instruction. Okay, now, good. Let me close this PowerPoint, which is not needed. Okay, perfect. Let me share the screen and a few words before moving into the lab. But before moving into the lab, and of course the online students cannot attend, I want to say a few words to say goodbye, and then we go to take a coffee after the lab. But just to say goodbye to you, a few words to all of you, because some of the students cannot follow us in the lab and at the bar afterwards. So you have the exam dates. I think it's clear to you how the exam is articulated. You have a test exam to try. If you are a non-engineering student, use the same test exam, but beware that there will be a separate quiz for you to be taken only by non-engineering students. Of course, there is a check on it, and which will be less details in terms of mathematics. And then remember, after the quiz, there is 5 minutes oral. I see that there are already many people subscribed for the first exam. This is fine. I think we should be able to make it the same day. If not, we will move to the next day. Okay. I think it will be anyway. One day will be enough. If you don't take the exam, please unsubscribe. It is extremely important that I get a picture, and I will send also an email to remind you, a picture earlier of how many students I have to make the exam. And if you have any question, just let me know. Okay, you can contact me by email. And I aim to reply as soon as I can, but please wait a few hours or maybe one day if you don't see any answer before sending the mail again. Usually I don't lose an email, but especially if you send it from your institutional account, it shouldn't go into the anti-spam. But in any case, if you don't see a reply after a couple of days, resend it. So, a few things to conclude. I want to thank you because you were the first students attending this program, I mean this course in the form it was delivered this year. And it is a mixed form, hybrid mode, with some lectures online, and the lectures are, most of them were newly created on purpose for addressing this topic. So I want to thank you because your attendance was always consistent, and also your reaction was better than I expected. So it was an interesting experience for me. If you have any suggestion for the next year to improve, I will see your feedback in the full season. But in any case, if you want to be more detailed and send to me some suggestions, I really appreciate them. Ideally, I would have preferred to have more time to dedicate to exercises, and so next year I will try to make the schedule a little bit different by maybe removing some of the parts. But I hope that you could get the opportunity also to see a little bit how this concept can be translated in practice. So again, thank you very much. If you have any questions related to the course now, please step in, also the students remotely connected. Otherwise, I say goodbye to the students and we move to the lab. Yes, please, a question?
I have two questions. First one, if you choose any here yourself, it's still only multiple choices, right?
Yes, it's still a brief with multiple choices. And as you see in the presentation of the course, there is no penalty for wrong answers and there is only one correct answer.
And will the exam be computer lab?
Yes.
Or do you bring your own computers?
I think I booked a computer lab. Yes, I booked a computer lab. So you don't need, at least for the first one, you don't need to bring your PC, but in any case, I will put on Amazon a note to confirm everything. Okay?
Thank you.
Other questions? Okay. So thank you, students, remote students, and thank you once again. And if you have any question, you can tell me.
Thank you, Professor. Goodbye.
Bye-bye.
Thank you. Bye-bye.
Thank you. Bye.